Okay, welcome to Let's Get to the Marks, people. Going through an A-level chemistry alcohols question pack. This is the walkthrough part 2. Check out my part 1 to this pack on alcohols. You can check that out here, and let's get into it. In the UK, industrial ethanol is now produced by direct hydration of ethene. This process has largely replaced the fermentation method. What is the likely reason for the change of method? The direct hydration of ethene produces pure ethanol. Direct hydration of ethene, the direct hydration route employs milder conditions. The direct hydration route does not use a catalyst. The direct hydration route produces ethanol by a slower reaction. Here's the general equation for the reaction of ethene with steam to produce ethanol. This is the industrial method. Let's go through these and see which one's the right answer. Well, you can see here that the direct route just produces pure ethanol. The problem with the other parts of this question is that each one of them, like for instance, fermentation with yeast is the alternative method. The problem at the end of that is that you've got yeast floating around in your product, which is your ethanol. You use glucose and yeast, and once the yeast have turned all the glucose into ethanol, the problem is you've got to separate your old yeast from the ethanol. So the product isn't pure. And if you want alcohol for hand wash and for various other products, you've got to go through the laborious process of getting rid of the yeast. So top one is the correct answer. Let's look at why the other answers are incorrect. So for part B, the direct hydration route employs milder conditions. Well, that's not true. We use 300 degrees in the industrial production of ethanol. You don't have to be exact, but it's a very high temperature, up to like 300 degrees. And we use a phosphoric acid catalyst. So that takes out C, which was the direct hydration route does not use a catalyst. No, it does. It uses a phosphoric acid catalyst. And then can we say if it's at 300 degrees for part D, can we say it's going to be slower? Doing this reaction at 300 degrees with a catalyst, it's going to happen very quickly. Whereas when we do the fermentation of yeast, we use 30 degrees because we have to be aware not to denature the enzymes within the yeast. So we have to use a lower temperature. So the fermentation method is going to be a lot slower. So the only correct one there is A. Let's move on to the next question. Okay, let's zoom in a little here. Question 9. Cyclohexene has a boiling point of 83 degrees and can be prepared by the dehydration of cyclohexanol, boiling point 161 degrees, using concentrated phosphoric acid. Here we can see we've got the reaction of cyclohexanol being turned into cyclohexene with the removal of water. A student prepared cyclohexene by placing 10 centimeter cubed of cyclohexanol of a density of 0.96 grams per centimeter cubed in a round bottom flask. 3 centimeter cubed of concentrated phosphoric acid were then carefully added to the flask. The student added a few anti-bumping granules and set up the experiment as shown here. So you can see we've got the flask, the Liebig condenser, all shown there. Let's go through the method. The student heated the mixture and collected the liquid that distilled at temperatures below 100 degrees. The distillate was poured into a separating funnel and washed by shaking with sodium carbonate solution. Periodically, the separating funnel was inverted and the tap opened. The aqueous layer was discarded and the final organic product was dried using anhydrous calcium chloride. After the product was dried, the drying agent was removed by filtration under reduced pressure. The student collected 5.97 grams of cyclohexene in the experiment. Calculate the percentage yield. So we just got to remember that there was 5.97 grams of cyclohexene produced. I'm going to do the calculation up here where I can actually see the equation. Okie dokie. Let's have a little look here. The student prepared cyclohexene by placing, we've got 10 centimeter cubed of cyclohexanol density 0.96 into a round bottom flask. Check out my round bottom flask, bit dodgy that. So they whacked in 10 centimeter cubed of the cyclohexanol, which is the reactant. So they're sticking, I'm circling it here, they're sticking the cyclohexanol in there. And it tells us that the cyclohexanol has a 0.96 gram per centimeter cube density. Now, that means I can use a couple of equations here to work out how many moles of cyclohexanol, of the reactant I'm starting with. I'm going to need mass over mR times moles, and I'm going to need density times volume equals mass. So the first job is to use the density to find the mass. So we're going to do 0.96, which is the density, times the volume, 10 centimeter cubed, gives me a mass of 9.6 grams. Now I can bring that over here, work out the MR of cyclohexanol. So there's 6 carbons, an OH, 1 H coming off there, and 2 H's off of every other carbon. So what's that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 H's. So C6H12O. So we need to work out the MR of cyclohexanol. Then we can do mass over MR. So 6 times 12 is 72. Plus 12 is 84. Plus 16 is 90, is 100. So the MR of cyclohexanol is 100. So now what we need to do is mass over MR. So 9.6 divided by 100 is going to give us 0.096. Now we have the moles of the cyclohexanol, the reactant. We need to work out what's the maximum amount of moles of cyclohexene, the product, we can produce. Well, it's a 1-to-1 ratio. We can see that from the equation. There's no coefficients. So that means we're going to get 0.096 of cyclohexene. Now that we know the moles of cyclohexene, we can go back to our triangle with mass over MR times moles and do moles times MR. We've got to work out the MR of the cyclohexene. So once again, I like to just scribble on the diagram. There are 6 carbons, obviously, C6. Working out the hydrogen's a little bit more difficult. It's not a straightforward alkene where you just times 2. Cycloalkene has slightly less hydrogens because those carbons with the double bond have to also attach to another carbon. So we're going to go C6H10, which is 72, plus 10 is 82. Total for the MR. So we want to do 0.96 times 82. And what is that going to give us? That's going to give us, I can't fit it in on the blooming page. That's going to give us 7.872 grams. So we've got 7.872 grams. I now want to do percentage yield. Remember that yield is equal to the actual mass, which was 5.97 from down below. We saw that. Over the theoretical maximum mass. The theoretical maximum mass was 7.872. So I want to do 5.97. That was the grams that they actually got from their experiment. Divide it by the amount they should have got, or the theoretical maximum, 7.872, times 100, and I basically get 75.83%. Now you can round that in your calculator, but on the mark scheme they expect anywhere between 75 and 76%, anywhere between 75.8, sorry, and 76% they're accepting in the mark scheme. So that's nice. That's going to get you all 3 marks. Lovely jubbly. Right, let's zing down. I'll just scribble it here. What did I say? 75.83 or 84, whatever. It was between 75.8 and 16%. 70, sorry, and 76%, not 16%. Right. Describe a test tube reaction on the product. Remember, the product is an alkene to show that cyclohexanol being dehydrated. So how do we know that we've definitely produced an alkene here? How do we know we've got a double bond? What's the test for the double bond, the carbon-carbon double bond? Hopefully you should all know. We want to use bromine water. So you could write BrAQ, or you could just say bromine water, or you could just say add bromine, because you could do it in a fume cupboard, because bromine vapors are a little bit dangerous. So you can use bromine water, and it decolorizes from orange, obviously, to colorless, which is what you get when you decolorize something. So bromine water's orange, and it decolorizes as the bromine adds across the double bond. Okay, the next question. Suggest why sodium carbonate solution was used to wash the distillate. So why did they use sodium carbonate? What do we use carbonates for in organic chemistry? Obviously, they can be used as an analytical tool. They can test for acids. In this situation, we're using the carbonate to remove acidic impurities. And if you look at the method, the acidic impurity here says somewhere in the stem. Where is it? Where is it? There it is. 3 centimeter cubed of concentrated phosphoric acid. Now, this is a catalyst. So if we have any of this phosphoric acid left over, which we will do, it's a catalyst. So we need to remove it. And we can do that by adding sodium carbonate solution. So to remove or react with any acid. And the next question, D, says, why is it important to open the tap of the separating funnel periodically? Why do you think they need to take the top off of the apparatus every now and again? As we've just used sodium carbonate with acid, what's going to be a byproduct? What gas is going to come off, do you think? What's the danger if we let that gas just build up in the equipment? So obviously we're using a carbonate, and you should know when carbonates neutralize acids, they release carbon dioxide. Of course, they make salt water and carbon dioxide. So we're getting carbon dioxide released. That is going to cause pressure to build up within the equipment. And this is why we periodically take the top off to reduce the pressure and ensure we don't get an explosion, or our equipment doesn't crack or fall over, or the top doesn't blow out and stuff like that. So a little safety thing there. Of course, they said they'll invert it as well periodically as well. That's just to ensure that you've got an even mixing of all of the reactants, or all the mixture is spread evenly. Anyway, to relieve the pressure build up, we're taking the lid off, or with the top off, or opening the tap, sorry, periodically here to release some of the carbon dioxide from the carbonate we added to neutralize any acid. Right, we're going to move on to the next part. So, E, give a property of anhydrous calcium chloride other than its ability to absorb water that makes it suitable as a drying agent in this preparation. So whenever you want to get rid of water, we normally use water to get rid of soluble impurities. So you often have water hanging around in these methods, and you need to get rid of the water. So we add an anhydrous salt. And here they've added anhydrous calcium chloride to absorb the water. However, what else is it important? Like, what is another important property of the calcium chloride? Obviously, we don't want our drying agent to react with our product, and our product is cyclohexene. We don't want something that's going to try and add across the double bond or react with the cyclohexene, and calcium chloride won't react with it. So that is another important property of a drying agent. Not only does it need to absorb water, but it shouldn't react with your product either. Describe the apparatus used to remove the drying agent by filtration under reduced pressure. Your description of the apparatus can either be a label diagram or a description in words. So we want to place the drying agent with the solution in the top of some filter paper in a Buchner funnel. Now, a Buchner funnel can then be attached to a flask with a vacuum pump coming out the side. So we've got our Buchner funnel here, and you're going to have dotted line represents your filter paper, got your drying agent up there, and then the flask below will fill up with your all the stuff being drawn through, and then you have a pump, well, a vacuum pump that's going to create the suction to pull all that liquid through and remove your drying agent, which will be left behind on the filter paper. Okie dokie, we're nearly done. So this will get you 2 marks. You can have a combination of words and the diagram combined as well. Right, let's go. What's the next question? Where are we? Here we are. G. A sample of cyclohexene has been contaminated with cyclohexanol. The cyclohexene can be separated from the cyclohexanol by column chromatography. Silica gel is used as the stationary phase and hexane as the mobile phase. Explain why cyclohexene has a shorter retention time than cyclohexanol. Well, the solvent here is hexane, C6H14. It's non-polar. It's just made of carbon and hydrogen, which have very similar electronegativities, and so it's not a polar molecule. The fact that cyclohexene is retained less time on the silica gel means cyclohexene spends more time in the solvent, the non-polar solvent. The fact that means then cyclohexanol must be the more polar molecule, and it must mean that cyclohexanol, because of the OH group, it's polar, the hydroxyl group, it's actually being retained on the silica gel more. It has a stronger affinity for the silica gel, the stationary phase, than it does the mobile phase, because the mobile phase is non-polar. Now we can write it like that, like I've done there, or you can write it in the other context where we talk about hexane's a non-polar solvent. Therefore, cyclohexene, which is a more non-polar molecule, it doesn't have that hydroxide bond, that electronegative oxygen and electropositive hydrogen. It doesn't contain that. So it's more non-polar than cyclohexene. Therefore, it has a higher affinity to the solvent, which is non-polar, or the mobile phase. And so it spends less time being retained on the silica gel, which is the stationary phase. So it spends less time on the stationary phase, and that's why it has a shorter retention time. H. Explain how an infrared spectrum would confirm that the cyclohexene obtained from the chromatography column did not contain any cyclohexanol. So the way to confirm this is to look at our data book, which comes with your exam, and check out if there's an OH bond on the infrared spectrum. So let's get that up now. So what we're doing here is we're checking to see if any of our reactant, our cyclohexanol, is there where it shouldn't be in the product. And if it was there, we'd expect to see that OH bond between 3,230 and 3,550. And so if we have only made cyclohexene, we should see no peak representing that OH bond. And that's the end of the second part, or part 2 of my alcohols pack. So check out the third pack. Let's get to the marks.
You're still here? It's over.